Hey everybody, Mr. Klein here. This time I am not wearing a hat. Today we're going to be talking about graphing the derivative. The big idea for today is you want to have a function and you want to be able to figure out what the value of the derivative would be at lots of different points. If you can do that, then you can graph the derivative. So let's begin here. We've got a function. What kind of function is this? That's right, it's a quadratic function. I've drawn it right here. What we're going to do is find the derivative at 0, 1, 2, 3, and 4. Now I'm going to suggest to you that one of those derivatives you can find just by looking at this picture. Can you tell me which one that would be? That's right, it's at 2. If you look at 2, that's where the vertex of the parabola takes place. We know that at the vertex we have a horizontal tangent line, which means that we know immediately that the derivative would be 0. Let's go a step further. If we look at the values of the derivative before 2, so at 0 and 1, what should we be able to tell about the derivative because the function is decreasing? That's right, the slope is negative, and on the other side, anything larger than 2, the slope is positive. So now let's actually calculate one of them. It doesn't really matter which one we pick. Let's say we find the derivative at 3. Recall from last time, the way we go about this is we say that the derivative at 3 is equal to taking a difference quotient, where one of our points is 3 comma f of 3, and our other point is x comma f of x, and then we take the limit as the x value approaches 3. This formula will give us the actual value of the derivative. Once you've written that, the second step is to replace f of x with the actual function. And to replace f of 3 with its actual value, which is, I'm just going to get it off of the graph here, 1, 2, 3, 4, 5. The next thing that we do is we say, well, 8 minus 5 would give us a 3, and then we should be able to factor. When we factor, whatever factor we see in the denominator should be a factor of the numerator. So I have up here x squared minus 4x plus 3. That should factor into x minus 3 and something else. In this case, it'll be x minus 1. The x minus 3's cancel. We are left with the limit as x approaches 3 of x minus 1. So we plug in 3 minus 1 equals positive 2. So the slope right here is positive 2, and that's kind of what we expected, right? When we looked here, we knew that it was going to have a positive slope. So I went ahead and I found the derivatives at 0, 1, and 4, and I got these numbers. Negative 4, negative 2, and 4. What do you notice about those numbers? Hopefully what you notice is that they make a linear pattern. In fact, look at this. If we graphed the derivative, we would graph it by saying at 0, the value is negative 4. At 1, the value is negative 2. At 2, the value is 0. At 3, the value is 2. And at 4, the value is 4. So the derivative graph looks something like this. There it is. We just graphed our first derivative. Now here's what I have noticed. The function was a quadratic, and the derivative was linear. Okay. Well, here's some things that you learned in your last lesson. If a function is linear, right, if it looks like that, then the slope is never changing, so the slope is constant. And if the original function is constant, then the derivative is 0. So we've got this pattern going on where here, if you think about this, the degree is 2, the derivative has a degree of 1. Here, the degree equals 1, and the derivative would have a degree of 0. So what's happening when we take the derivative? 2 goes to 1, 1 goes to 0. That's right. If the degree here is n, then the degree here would be 1 fewer. It would be n minus 1. All right, ladies and gentlemen, I would like you to read this paragraph to yourself. Pause the video. Now that you've read it to yourself, a couple things that we can note on here. First is that the x-axis is measuring time that has gone by. And second is that the d does not mean distance, it means degrees. And we're talking about a door. A door is being opened and closed. So I want you to tell me how, based on this picture, is this door opening and closing? Here's a door. I'm going to open and shut this door, and I want you to tell me which version of opening and shutting the door is described by the graph that you're looking at. So here's A. Here's B. And here's C. So that's right, the answer was B. The reason it was B is because we can see right here that the door opens very quickly. We have a steep slope, and then it closes slowly because we have shallower slopes. Other things that are worth noting is that since our goal is going to be to draw a picture of the derivative, at this maximum right here, that's when the door is the most open, we can say that the door is neither opening nor closing. So its rate of change is 0. You can also see that because if you look at the graph, you'll note that the slope of the tangent, which I am drawing on right here, is 0. So when we draw our graph of d prime, of the derivative, we know that this point right here is going to have to be on that graph. Another thing we know is that when the door is opening, the rate of change is positive, so we're going to have a positive derivative graph. And that here, where the door is closing, the rate of change is negative, the slopes are negative, so we will have a negative derivative graph. In your calculator, I want you to draw a picture of this thing. The way that you're going to do that is, and you might need to pause the video a little here, you're going to type the function into I1. Then you're going to go to Window, and you're going to go 0 to 10 because our x interval goes from 0 over here to 10 right here. Once you've done that, you will hit Zoom, Fit, and our calculator will draw the graph for you. It's not going to give you any of this negative area down here, but it would be useful if you could see that. So let's go back to Window, and let's change the minimum y value down to -40. That should get you what you want, and then hit graph one more time. All right. So there's your graph. Let's move forward. We want to get a picture, and I'm going to say let's start by getting an idea of what the derivative is here at 1. Now, I know that it's positive. Doesn't look like it's going to be a very large positive number. One way that we already know for estimating the derivative at that instant is to use a tolerance of 0.001. You can't use our new tool, that formula that I gave you last class, because this function, what is it, 200t times t to the, or 2 to the negative t, that's, it's not a polynomial. So that formula is not going to be helpful to us. So instead, we're going to go d prime of 1 is approximately, and then we're going to use the number of degrees at a time ever so slightly larger than 1, and then at 1, and then we're going to divide by the change in time, which would be 0.001. Keep in mind that if you've done a good job typing things into your calculator will do this work for you, and we can enter this in all in one fell swoop by saying alpha trace of y1, 1.001, minus alpha trace of 1, all divided by 0.001. Okay, so we get 30.6. We'll round that off to. And probably the most important part of this class is being able to describe what that means. Well, our numerator is in degrees. So our units will be in degrees divided by our denominator is in seconds. So this is degrees per second. So 1 second after we open the door is opening at a rate of 30 degrees. You can kind of picture how big 30 degrees would be, at a rate of 30 degrees per second, or 30.6 degrees per second. Next thing, check this out. It turns out that the work we did right here, the calculator will do for us. There is this feature called nderiv. It's right here. You hit the math button, and then you groove on down to number 8. When you get there, here's what you're going to put in. I would write this down for future reference. You'll see dd space. You're going to put an x into that space of the function that we are working with. So we typed our function into y1 already. You could, if you wanted to, type the actual function 200x times 2 to the negative x into that space, and that would also work. And we want the derivative at a particular instant, and that instant is at 1. When we do that, it's going to give us a number, and what do you know? Boom, 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 boom. Basically the same thing. And this is, in fact, more accurate than what we got right there. Good stuff. So I'm going to come up here, and I'm going to mark this point on the graph at 1, 10, 20, 30.6. We know that point is going to have to be on the graph of the derivative. Now let's go to 2. If we wanted to find the derivative at 2, what do we know about the derivative at that instant? One of the cool things about our grapher is we can just come up here, copy this formula, and then enter a 2, and it will give us the derivative at that instant. So negative 19.3 is the derivative at 2. That means that at that instant, the door is, that's right, the door is closing at a rate of 19.3 degrees per second. So that would put us, let's see, negative 10, negative 20. We're about right here. I'm going to go ahead and connect this chunk of our derivative graph. Next thing I want you to see on the calculator is that we can draw this whole thing. Here's how we're going to do that. You go to y2, and in y2, you choose n deriv. And same idea, you hit an x, and then here you go y1. So we're graphing the y1 function's derivative with respect to x. That's what you call this. Now here's the tricky part. If you put a 1 right there, or you put a 2, you're just going to see a horizontal line, because all it's going to do is graph whatever the value of the derivative is at that one moment. We want the derivative at every single moment. So what should we choose as x? You want to put in x equals x. I'm actually going to write this down up here just so we have a reference. y2 okay, there we go. All right, are you ready? I'm going to graph this thing. Another thing I'm going to do, let's see, am I in a different color? I am in a different color. That's good. So here we go. Here is the graph of the derivative. Notice that it is positive. It becomes 0 right at that instant when we knew it would become 0. It is negative afterwards. Ooh, this is interesting. It goes down, it hits a minimum, and then it starts to come back up. Let's draw that derivative on our graph. So it's positive over here, comes down to a minimum somewhere, and then turns around and comes back up. Now the last piece is I want you to know something about this derivative, or at this. Now the last piece is I want you to know something about this minimum right here. So draw a vertical line. And you'll notice that this minimum links to an interesting point here on the original function. If you look here to the left of it, over here the graph is concave up, and over here to the right of it, the graph is concave down. And here in between them is that point where the graph changes from concave up to concave down. So this is called the point of inflection. Now, the next thing that I'm going to say is pretty important, and I don't have a better way to describe it than to just like kind of show you the picture. If you look at what's happening over here, think about the slopes. Slope is 0, negative, more 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 negative. We hit the point of inflection. One thing that's interesting at the point of inflection is that if we drew the tangent line right there, it actually kind of moves through the graph so that it's above the graph on one side and it's below on the other. Now, there we have a pretty negative slope. Afterwards, the slope is less negative, and then less negative, and then less negative, and shallower and shallower and shallower and shallower and shallower and shallower. So the point of inflection is the instant where we have the steepest slope. Oh, well, doesn't that make sense? That at the instant when we would have the steepest slope, that's when down here you would have an extreme value for the derivative, right? If this is the steepest, then that makes sense that it would correspond to a minimum on the derivative. by the way, I should probably mark. This is d of x right here. This one is d prime of x, or I guess it's d prime t that we're talking about. All right, so what did we learn from doing this investigation? Well, we learned a couple of things. First, we learned that when the function has a maximum, the derivative is going to be 0. Now, where else would that be true? That's right. It's also true at a minimum. The other thing we figured out is that if the function has a point of inflection, that's where it will have its steepest slope, which means what will be true on the derivative. That's right, the derivative will be at a maximum or a minimum.